This video is going to be all about energy conservation. So the idea of energy conservation is that our initial energy plus any work done is going to equal our final energy. So this work has three options. It can either be positive work, so some external force that is in the same direction as a change in height. We can have negative work, which might be something like friction, or we can have zero work. And usually the zero work is what we're going to be talking about. Okay, so that's a major idea behind energy conservation, is the initial energy plus any work done gives us our final energy. Okay, so we usually were writing this out as PES initial plus PEG initial plus KE initial equals PES final plus PEG final plus KE final. Now, our system might not have all of those types of energies. We might not have all of them in the beginning. We might not have all of them at the end. We might only have one. We might only have two. It all depends. So it's important that we cross out or cross off what the system does not have. Now, I'm not talking about the problem. I'm talking about how the problem defines the system. So even if there's a spring in the system, if there is no, or sorry, even if there's a spring in the problem, if there is no spring in the defined system, then there is going to be no spring potential energy. Okay? If there is no earth in our defined system, then there is no gravitational potential energy. And instead, those things, while they do act on the, say, cart or mass, while those forces, like the force of gravity and the spring force, do act, instead of changing the gravitational potential energy or spring potential energy, they're going to change the total energy of the system, okay, instead of having energy conserved. Okay. So remember to cross off what the system does not have. Okay. So let's talk general problem-solving process. Let's say we have a cart that is on top of a hill moving with a speed v, and then it comes to the bottom of the hill, and we're trying to figure out what the speed at the bottom is. Okay. Anytime your system changes position or something like that, it's a pretty good hint that we're going to need conservation of energy. So the first thing you want to do is identify two locations or positions in time. Okay. So let's say this is position A and this is position B. And I'm going to define position B at being at a zero height. Okay. And position A, the problem will likely tell us, has a height h or something like that. Okay. So once we have our two locations defined, it's important that we define our system. So let's say our system is the cart earth system. Okay. So in the cart earth system, the energy at A plus any work done by an external force should equal the energy at B. But because the earth is in our system, there are no external forces because we are going to assume that this is a frictionless surface. So that W should go away. So now I have to think about what energy or energies do I have at A, what do I have at B? Well, at A, I am moving, so I definitely have a kinetic energy. And I'm at a height, so I also definitely have a gravitational potential energy. There's no spring even in this problem, so I shouldn't include spring potential energy. At B, I've defined B as the zero height, so that means there's no gravitational potential energy. So I only have a kinetic energy at B. So I have 1/2 mVA squared plus 1/2, nope, that's wrong. mgh is 1/2 mvb squared. And this will help me solve for the VB. Now, a lot of you get kind of cancel happy with the masses. You can only cancel the mass if there is a mass in every single term. And what do I mean by term? I mean every single thing that I'm boxing, essentially. And there is a mass in every single box, so I can cancel mass. So I have 1/2 VA squared plus GH is 1/2 VB squared. And the consequence of canceling the mass means that the mass is not going to determine anything about the velocity at B. So it doesn't matter if it's a big cart or a little cart. Mass doesn't matter. The velocity is still going to be the same. Okay, so from there, I would multiply both sides by 2. Okay, so I would have 2, 1/2 VA squared. GH is VB squared. And then I would square root both sides. And that would give me an answer for VB. It's not pretty, but that would be the answer. Now, let's say the question defined our system as the cart only. Okay, cart only. So again, we have the energy at A plus any work done is equal to the energy at B. Now, if our system is the cart only, that means that the work or the force of gravity is doing work. Okay? So in this case, we can say that mechanical energy is not conserved. Okay? Whereas here, mechanical energy is conserved because there's no external forces. Okay. So you might be thinking, okay, well, the work done by gravity, is that going to be positive or negative? Well, if we remember, gravity always points straight down, and we're moving down, so this work is going to be positive, okay? Which means that our mechanical energy at A is going to be less than our mechanical energy at B, which makes sense because if there is no gravitational potential energy, then the only energy we can really take into account is the kinetic energy. Right? We are definitely moving faster at B than we are at A, so this makes sense. Okay? Again, that's what happens if our system is defined as the cart only. If we are the cart-Earth system, we can include gravitational potential energy and mechanical energy is conserved. So another system we might see is a spring that is attached to a wall, and then there's some ramps. So we might have a mass pressed up against the spring at rest, and then at some later point, the mass is moving with a speed v, but the spring is no longer attached, and then it rises to some maximum height where it momentarily stops. So again, we have our system changing positions. So it's a good idea that we need conservation of energy, but this time we're going to have 3 positions, so in A, B, and C. Okay. So let's say that we are the spring cart Earth system, and this is a frictionless surface. Okay. So if we are the spring cart Earth system, then energy is conserved, which means our energy at A has to equal our energy at B, has to equal our energy at C. At A, since we are at rest and a spring is compressed, we have spring potential energy. At B, we are moving free of the spring, but not at any height, so we just have kinetic energy. So all of the spring potential energy has converted into kinetic energy. And then at C, we are at a maximum height, free of the spring, moving at a speed 0. So we are just gravitational potential energy. Okay. So the initial spring potential energy converts to kinetic, and that kinetic then converts or transforms into gravitational potential. Okay. Remember from math class, if A is equal to B and B is equal to C, then A and C are also equal. So you could set the initial spring potential energy equal to the final gravitational potential energy. Okay. All right, so last thing I want to talk about in this video is some important relationships. Okay, so let's say we have a system that is converting between gravitational potential energy and kinetic energy. I'm putting a double arrow because it doesn't matter which direction it's going. Okay, remember, if those are the only two types of energy we have, then mass can cancel. Mass can cancel. Okay, so we're essentially converting MGHs into 1/2 mv squareds. And again, these are maxes. Okay? There are going to be instances in between where we have some potential and some kinetic. So again, mass can cancel. The important relationship I want to point out here is that H isn't directly proportional to V, but proportional to V squared. So if I double the velocity, then that means I'm going to quadruple the height. That also means if I want to double some final velocity, I need to quadruple some height. Okay? If I double the height, then that's only going to lead to an increase of a square root of 2v, not 2. Okay? Because we could also say that v is proportional to the square root of h by just square rooting both sides. Okay? The other relationship I want to talk about is spring potential energy converting back and forth to kinetic energy. Here, mass does not cancel. Okay, really important. Mass matters here. Mass matters when we're involving spring potential energy. Okay, so we have a 1/2 kx squared converting to a 1/2 mv squared. The 1/2s at least cancel. Okay, and here x squared is proportional to v squared, which actually means that x and v are directly proportional. So if I triple x, then we are going to triple the velocity. But remember, if I triple x, then the total energy is 9 times as great, because remember, the total energy is set by either the kinetic energy or the maximum spring potential energy. So if I triple x, x and e total have a squared relationship, so I got to square the 3. And that is it for the energy conservation video. Have a good day.